So with last lecture's foray into the world of all things application, this part, we're going to step back and look at some more theory. Okay, and here's my question, and it involves higher order derivatives, and here's the idea. We can take the derivative of a function, right? We can take the limit as h goes to 0 of f of x plus h minus f of x over h, right? You know, fairly routine stuff in a certain sense. But could we take the derivative of f prime, right? Could we calculate the limit as h goes to 0 of f prime of x plus h minus f of x all over h? Well, sure, right? How would we notate that, right? So my point here is that there's nothing stopping us from doing this, but then the question, of course, is does it matter? Does it give us any useful information? And the usefulness of the information will come a little bit more later in our course. We have one or two interesting applications here. But first, before that, a note on notation, right? So we have our function, f of x, right? If we want to take the derivative of it, we saw a number of ways to do that, right? We could write f prime of x, we could write, d sub x of f of x, or just d of f of x, or, y prime, or dy dx, okay? If we want to take another derivative, right, the derivative of the derivative, it's often called the second derivative, right? Then that would make this the first derivative. And we can denote that f double prime of x, right? Or d squared of f. Or y double prime, or, and this is, I think, the weirdest one, okay? D squared y over dx squared, okay? If we're taking a third derivative, right, we're going to go into f triple prime, right, d cubed, y triple prime, and just as before, d cubed y over dx cubed. One thing that's important to note, I'll just let these two sort of continue down, right, into, say, the nth derivative, right, because you can continue this process as much as you want. So I want that one to continue down. D to the n of y over dxn, right? After 3, f, it stops being f, quadruple prime. It's just the fourth derivative, right? In parentheses here, right? To distinguish from, f cubed, right? It's f, with these parentheses, the nth derivative of x, and the nth derivative of y, okay? So let's apply this to a specific example, okay? Let's take, or rather, let's find all derivatives of, we'll say, f of x is x to the 5th minus 3x to the 4th plus 4x cubed minus 2x squared plus x minus 8, okay? Well, first, we should take our first derivative, right? Which is going to be, looks like 5x to the 4th, 12x cubed, 12x squared, right? Minus 4x plus 1, right? Our exponents drop down and get decreased by 1. Okay? If I want to find the second derivative, I'm taking the derivative of the derivative, right? So my 4 is going to drop down, multiply by 5 to become a 20x cubed. My 3 is going to drop down, multiply by 12 to get a 36x squared. My 2 drops down for a 24x. My 4x just becomes a 4, and my 1 becomes a 0. Okay? What about a third derivative? All right, well, my 3 is going to drop down, give me 60x squareds. Minus 2 times 36 is going to be 72x's. 24 left over, my minus 4 drops. My fourth derivative of x, 120x's, 72 left over. What about my fifth derivative? Well, my 72 is going to drop, and we're going to be left with 120. What about my sixth derivative? Well, it's just 0. What about my seventh derivative? Well, the derivative of 0 is still 0. So that means I can actually take this down here and say the nth derivative of x is 0 for n strictly greater than 5, right? So what this means is we've categorized all of them, right? If it's the first derivative through the fifth derivative, you look here. If it's anything higher, it's just 0, right? So we've categorized all of the derivatives, okay? Let's take a look next at, I don't know, let's find the third derivative of, say, f of x is x to the 2/3, right? We can still use our power rule here. It's a little bit more involved, right? Because, things don't quite cancel as easy when you have fractional powers here, but we can still chug along, right? F prime of x, my 2/3 is going to drop down, and we're going to have x to the 2/3 minus 1 for minus 1/3. Our second derivative, we can continue the same process, right? Our negative 1/3 is going to drop down. Looks like we're going to get a negative 2 over 9 x to the, now when I subtract 1, I'm going to get minus 4/3. It's our second derivative. And then for our third derivative, the one we're looking for, we're going to get negative 2 over 9 times negative 4 over 3. And then x to the, we need to subtract 1 again. Looks like to the 7/3. Okay, and then cleaning this up a little bit, looks like we're going to have 8 over 27, x to the negative 7/3. Okay, we'll do one more of these, just one of the computations. In this case, find the second derivative. We'll say of g of x is 2x squared plus 3 to the 3/2. Okay, we have to use the chain rule for this one because we've got, a fractional power. So we'll say what g of u is, well, I guess first we should say u is 2x squared plus 3, right? So then u prime is 4x, right? G of u is going to be u to the 3/2, okay? And then g prime of u is going to be 3/2 u to the 1/2, okay? And then that means that g prime of x is g prime of u times u prime, right? Which is going to be 3/2. Now we do all of our substitutions. 2x squared plus 3 to the 1/2 times 4x, okay? And if we simplify that, right, we're getting 6x times 2x squared plus 3 to the 1/2. But we need to take a second derivative, right? So I'll copy down our first derivatives. 6x 2x squared plus 3 to the 1/2, right? And now we need to take our derivative again. And in order to do that, we need to do the product rule, right? And the chain rule, actually. We'll need to do them both. So the first one, d dx of 6x times 2x squared plus 3x to the 1/2 plus 6x times d dx of 2x squared plus 3 to the 1/2, right? This one on the left here is fairly easy, right? We're just going to get 6 times 2x squared plus 3 to the 1/2, right? And then we're adding on to that 6x, and we need to do our chain rule, right? So we'll let u equal 2x squared plus 3, and then u prime is 4x, right? And then we're going to have, I guess we'll need to call this guy h of u, right, is u to the 1/2. H prime of u is 1 over 2 times the square root of u, right? And then we can put all that together, multiply these two, substituting in our value for u, and we're going to get 6 times 2x squared plus 3 to the 1/2 plus 6x times what? Well, we're going to have 4x on the top, and then 2 times the square root of 2x squared plus 3, right? And now we need to clean things up a little bit and see, if anything, factors, okay? So here's how I'm going to actually write this, okay? If I simplify all of this, I'm going to get, well, my left-hand one can stay the same, but I'm actually going to write the other one as 12x squared times 2x squared plus 3 to the minus 1/2, right? And what that's going to allow us to do is we can now factor out, right, a 6 times 2x squared plus 3 to the minus 1/2, right, from both of these, okay? And then out of this one, right, we just get a single copy of 2x squared plus 3, right? And then out of this one, we're just going to get a 2x squared, okay? And once we run through all of this simplification, right, this guy's going to go down to the bottom, and then these are going to have some common factors. It looks like we're going to get 6 times 4x squared plus 3 over the square root of 2x squared plus 3, right? That's our second derivative. It looks substantially cleaner than one would think, you know, when you're going through all of this process. It's a single fraction. As I've said, after the exam, you know, we'll spend a little bit more time exploring the second derivative and its sort of geometric implications and what we can, you know, do with that. But for now, right, just based on purely definitional things, the second derivative measures the rate of change of the first derivative, right? The third derivative measures the rate of change of the first derivative, and so on, right? And one of the immediate implications of this, right, is when we look back at our train, right, we had a function modeling position. The rate of change of position is our velocity. The rate of change of the velocity, right, is the acceleration, right? So say you're on the roof of a building, right, and you throw a ball straight up in the air from the roof of the building, and then measure its height from the ground, right? You're doing something like this with a ball, right? Depending on how fast you throw and how tall the building is, right? We'll say that the position, right, S is what we've been using for position, is modeled by this guy, minus 16t squared plus 24t plus 120, right? Let's say we want to find the velocity and the acceleration at t equals 3, right? Well, here's what we know, right? My velocity, that's my change in my position over a change in time, right? And we have a function for s, right? So that means we just need to take the derivative of s. So what we're going to get negative 32t plus 24. That should be a t, right? Plus 24t plus 120. So our velocity is negative 32t plus 24. Further, as we said, my acceleration is my derivative of my velocity, or my second derivative of my position, right? So that means we need to take d dt of negative 32t plus 24, which is just going to come out to negative 32. So that means that my velocity at 3 seconds was going to be negative 32 times 3 plus 24, which comes out to negative 72, right? And my acceleration at 3 seconds, well, it's just negative 32, right? So what that means is that at 3 seconds, our velocity is moving at 72 feet per second downward, right? That's what this negative. And our acceleration of this ball is 32 feet per second squared, but it's 32 feet per second squared downward always, right? Notice how our factor of time hasn't, it's all gone away, right? The derivatives have sort of taken it away, and it's minus 32 for all places in time. Here's another application that kind of gets a little bit beyond these basic physics problems, right? Say you're looking at the CPI, right? The consumer price index of an economy, right? And say you have it as a function, right? You get all your data and you put it in a function, and I don't know, maybe it's doing something like this. Maybe it's doing something like this, between 2 points A and B, right? We know, right, that if we take the first derivative, right, we're going to get the rate of change of your CPI. Further, right, we know that this quantity, I prime of C over I of C, gives the inflation rate of the economy at a given time. But what happens if I take the second derivative, right? That's going to give us the way at which this is changing, right? So it's going to give us the rate at which this is changing, right? What's important here is that it's possible, right, to have, say, the first derivative be positive, right, and the second derivative be negative, right, which would mean, right, for a fixed I of c, it would mean that the rate at which inflation is happening is decreasing, right? Or like it's inflating, but inflation is slowing, right? And from this, right, you could make all sorts of you know, accurate predictions about what's about to happen to the economy if this inflation is slowing, right? Let's do a more concrete example, right? Um, say some function I of t, right? We'll say it's minus 0.2 t cubed plus 3t squared plus 100 for t between 0 and 9, right? Say it gives us the CPI of an economy, and we'll say t equals 0 corresponds to now, right? T equals 0 is, 2021, okay? So the question is, we'll do two things, right? We'll first find the inflation rate in, say, 2027, right? So that's t equals 6, right? And then we'll look at our second derivative and see what that can tell us, okay? So we can see that I prime of t, right, it's going to be minus 0.6 t squared plus 6t, right? And then if we're looking for t equals 6, right, then my inflation is what, right? The inflation rate is going to be I prime of 6 over I of 6, right? When you work this out, I prime of 6 is going to come out to 14.4, and then I of 6 is going to come out to 164.8. It's going to give us approximately an inflation rate of 0.0874. Okay, so about 8.7%. Okay, it's like, okay, that's an interesting, right, piece of data, but what's my second derivative here, right? I double prime, well, it's going to be minus 1.2 t, looks like plus 6, right? So then if I say we're to calculate I double prime of 6, right, the second derivative at t equals 6, I'm going to go, it's going to come out to minus 1.2, right? 1.2 times 6 plus 6 ends up at minus 1.2. So what that means is that, yes, inflation is at 8.7%. However, we also know that I prime is decreasing, right? That's its behavior, because since its derivative is negative, it's decreasing, right? If its average rate of change at a point, if its average rate of change is negative, the only way for this to be the case is if around that area it's decreasing. And again, that's a thing that we will explore in great detail in the coming weeks. But this tells us that inflation is at 8.7%. But since this is decreasing, this is also, going to moderate and decrease over time as well. Um, that's going to finish it off for this lecture. So I will see you guys on Thursday.